Hi everyone, welcome back to my channel. My name is Omid Jazi. I'm an assistant professor of statistics. This is the third lesson for a short course on longitudinal data analysis. In the first two lessons, we'll learn what longitudinal data are and exploratory data analysis. In this lesson, I'm going to talk about one of the most important tools in statistics, which is linear regression models and how to connect it to longitudinal data. So let's first recall the form of a linear regression model. This multiple linear regression model expresses a continuous response variable as a linear function of p covariates x1 to xp, and beta 0, beta 1 to beta p are regression parameters or coefficients, and epsilon I is the random error. So let's look at a simple example. Suppose we measure long function for several subjects at different time points. We start by fitting a simple linear regression model where long function depends on time, and we treat all measurements as if they were all independent. In this model, beta 0 is the intercept and beta 1 is the slope of the model. So let's use R to generate some longitudinal data. Let's say we have 20 people each measure at 5 time points, and then we use data frame function to create the long format data structure and head function to see the first 6 rows of the data. Then we use LM function to fit a simple linear regression model, long function versus time, and summary function to have the output of the fitted model. So let's look at some of the output for this example and their interpretations. The estimate for the intercept is 100.84, which is the average long function at time 0 or baseline. The estimate for the slope is minus 2.82, which means that if time increases by 1 unit, the average long function decreases by 2.82. Residual standard error is 2.78. This is an estimate for the standard deviation of long function or error, and multiple R square is 68%, which suggests that the model explains 68% of the variation in long function. For linear regression models to be valid, we need the following assumptions. The first assumption is linearity, which means that the relationship between the response variable and covariates is linear. The second assumption is independence, which means that errors are independent. The third assumption is homostaticity, which means that the variance of errors is constant. And the last assumption is normality, which means that errors are from normal distribution. We can use the plot of residuals versus fitted values to check constant variance assumption. If we see a random scatter and no pattern in the plot, we can say that errors have constant variance, and we can use QQ plot to check normality assumption. If the points are roughly on a straight line, we can say that errors are roughly normal. So what if any of those assumptions doesn't hold, and how can we fix that? If linearity is violated, we can add a quadratic or a spline term to the model. If variance is not constant, we can use transformation or weighted regression. And if errors are not normal, we can try robust or non-parametric methods. But keep in mind that any of those solutions will change the interpretation of the coefficients and estimates. But here's the catch. In longitudinal data, repeated measurements from the same subjects are correlated. And if we don't take that into account, our model underestimates standard errors and overstates significance. To fix this, we can use more advanced models such as linear mixed models, which include random effects in model, and generalized estimating equations, which specify a correlation structure. So in summary, linear regression models explore a linear relationship between a continuous response variable and some covariates. For linear regression models, errors need to be independent, normal, with constant variance. We can use diagnostic plots to check those assumptions. However, linear regression models don't account for correlation in longitudinal data, and we need more advanced models such as linear mixed models and generalized estimating equations methods, which we will discuss in future lessons. In the next lesson, I'll talk about estimation and inference for longitudinal data. Thanks for watching. If you found this helpful, please subscribe for more lessons on longitudinal data analysis. See you next time.